Good morning, everyone.
Good morning, ma'am.
Om Sarveshwam Swastir Bhavatu, Sarveshwam Shantir Bhavatu, Sarveshwam Purnam Bhavatu, Sarveshwam Mangalam Bhavatu. Ladies and gentlemen, a very good morning to one and all present here. I, Dr. Radha Gupta, on behalf of Dayananda Sagar College of Engineering, Bangalore, extend my hearty welcome to all the resource persons from different corners of India and abroad, distinguished representatives from AICTE and DSCE, the participants from all over India to this AICTE Training and Learning Academy sponsored 5-day faculty development program on computational mathematics and artificial intelligence for engineers. It's my privilege to be your host this morning. I take immense pleasure in introducing the distinguished representatives of Dayananda Sagar College of Engineering, Bangalore and AICTE to the audience. We have amongst us Dr. CPS Prakash, Principal, Dayananda Sagar College of Engineering, Bangalore, Dr. Sanjay Mangal Gopal, Coordinator, Akshay Urja Abhiyan, former Associate Professor and Head, Department of Mechanical Engineering, Veer Mata Jijabai Technological Institute, Matunga, Mumbai. Ms. Ankita Gupta, Research Associate, University of Massachusetts, Amherst, USA, today's speaker for the first two sessions. Once again, a hearty welcome to all. Before we call to order our faculty development program today, let us take a moment to thank God for all we have been given and ask for his help to maintain our focus with determination. May I request Mrs. Suma Manjunath, Faculty of Mathematics, to invoke God with her melodious voice.
शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु पार्वती तनय मूर्ति शरणु मूषिक वाहना शरणु सिद्धि विनायका शरणु विद्या प्रदायका भट्टमुत्तिन पदकहारने बहुवज्रचतुष्टने भट्टमुत्तिन पदकहारने बहुवज्रचतुष्टने इट्टतोडुगेय हेमकङ्कण पाशाङ्कुशधारने इट्टतोडुगेय हेमकङ्कण पाशाङ्कुशधारने शरणु सिद्धि विनायका शरणु विद्या प्रदायका कुक्षिवहलम्बोदरने इक्षुचापनगिरिदने कुक्षिवहलम्बोदरने इक्षुचापनगिरिदने पक्षिवाहन सिरि पुरन्दर विठलना निजदासने पक्षिवाहन सिरि पुरन्दर विठलना निजदासने शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु पार्वती तनय मूर्ति शरणु मूषिक वाहना शरणु सिद्धि विनायका शरणु विद्या प्रदायका शरणु सिद्धि विनायका शरणु विद्या प्रदायका Thank you.
Thank you, Suma, for rendering this wonderful invocation. There is a powerful driving force inside every human being that once unleashed can make any vision, dream, or desire a reality. One such person is our beloved principal, Dr. CPS Prakash, a person with an extraordinary vision and a versatile leader. I take pride in requesting Dr. CPS Prakash, Principal, Dayananda Sagar College of Engineering, Bangalore, to welcome the gathering and share his vision about hosting such activities in our institution. Welcome, sir.
Good morning. It gives me immense pleasure to be part of the inauguration program of Atal FDP program, starting from today, from 13/12/2021 to 17/12/2021, on computational mathematics and artificial intelligence for engineers. Dr. Sanjay Mangal Gopal, Ms. Ankita Gupta, the resource person who is going to start the session immediately after the inauguration. The main coordinator, Dr. Radha Gupta, professor and head of the Department of Mathematics. Dr. N.K. Geeta, who is the coordinator along with Dr. Radha Gupta. The invited resource persons and all the participants. I am sure that this 1 week faculty development program is going to be very useful and will be very good value add to each of the participants. Now with the Government of India going in full steam for the implementation of new education policy NEP 2020, it becomes essential for each one of us as trainers in engineering school to update and upgrade the skill sets to be able to give what the students require from the point of view of the industry requirement so that the students become industry ready. From that point of view, I feel that the topic is quite appropriate, computational mathematics and artificial intelligence for engineers. I presume that each session will be quite interactive with the participants gaining much required knowledge so that they can go back and use this knowledge acquired over a period of 1 week for the benefit of students. I thank once again Dr. Radha Gupta for giving me an opportunity to be part of the inaugural session of the Atal FDP and wish all the participants very active participation. Thank you.
Thank you very much, sir, for your words of wisdom. Teamwork divides the task and multiplies the success. A continuous source of inspiration and a firm believer of teamwork, Ms. Ankita Gupta, Research Associate, University of Massachusetts, Amherst, United States of America, is the speaker for the first 2 sessions of this FDP on computational mathematics and artificial intelligence for engineers. I now request Dr. N.K. Geeta, Associate Professor Mathematics at Dayananda Sagar College of Engineering, to introduce the speaker to the participants. Dr. Geeta.
Yes, ma'am. Thank you. A pleasant morning and a warm welcome to everyone present here. I hope you all are happy and content. I'm Dr. N.K. Geeta, Associate Professor, Department of Mathematics, Dayananda Sagar College of Engineering, Bangalore. Ms. Ankita Gupta is on board with us today as a resource person. Ms. Ankita Gupta is a researcher in natural language processing and artificial intelligence. She is currently pursuing her doctorate studies at the University of Massachusetts in US. She is interested in computational science, social science, learning from limited data, and language understanding in general. Ms. Ankita acquired her BTech in electrical engineering from MNIT Jaipur. She is a ME graduate in machine learning, system science, and automation from the Indian Institute of Science, Bangalore. She also held research scientist positions in industrial labs, including Amazon and Samsung. She worked as an applied scientist at Amazon with Indian machine learning team. She was also a lead engineer in machine learning at Samsung R&D Institute. The project aimed at automating the process of fact-checking. Under this project, she worked on various NLP problems and techniques such as bias detection, static fact verification, machine reading comprehension, and summarization. She was also the executive trainee at Power Grid Corporation of India Limited. She worked at National Transmission Asset Management Center as an engineer, contributing towards integrating power grid substations pan-India to a common control center for operational convenience. She is also a gold medalist in BTech from MNIT Jaipur. She was ranked third with honors in ME at IIT Bangalore. And also she received the Samsung Citizen Award for an individual contribution and excellence at work, extraordinary commitment, leveraging and development of talent, extension of support and achievements beyond the functional scope. Ms. Ankita Gupta, I welcome you to the session to share your knowledge on challenges in artificial intelligence for social applications. Now I request our HOD, Dr. Radha Gupta, to share few words about the speaker. Thank you.
Thank you, Dr. Geeta. I think she has very elaborately spoken about the first resource person of this FDP. My dear participants, as Albert Einstein said, learn from yesterday, live for today, and hope for tomorrow. The important thing is not to stop questioning. Somewhere something incredible is waiting to be known. So you all participating in this Atal FDP are going to experience it soon. Wishing you all the very best. I request Ms. Ankita Gupta to take over. Ankita Gupta, over to you.
First of all, thank you, Dr. Radha, and thank you, Dr. Geeta, for the introduction. I'm honored to be present here and for this opportunity to speak to the audience. Let me start the session without any delay. Just want to confirm if the screen is visible to all the participants.
Yes, visible. Visible.
Good morning, everyone. The last few years have been really very difficult for many people across the world. The world has seen its worst ever pandemic in the last few decades, COVID-19. And to worsen even things more, the digital ecosystem helped supported the spread of misinformation, that is fake news and false rumors about this deadly disease. Many people were affected by this wrongly circulated information, such as cold weather can kill coronavirus, or coronavirus can be transmitted through mosquito bites. As all engineers, we have gathered today here, and I want to ask you this question. Can AI help to handle such problems such as misinformation? Today's talk is going to be about AI for social good as a broader objective and to understand its challenges while we use this tool of AI and machine learning to handle such system critical problems such as misinformation, especially in the context of COVID-19. So for today, I want to help from all of you guys to help make me make a fake news detector. The problem looks simple. We'll start with some fake news articles, and we'll feed it. We'll generate a classifier today. We'll train this particular classifier. We'll in particular use a neural network. And using this neural network, we will then predict whether a given input article is fake or is it real. Before we go into the classification and neural, before we actually go into this, the whole objective of making this fake news detector, I'll briefly cover the classifier and the neural network details in the first session, followed by a hands-on experience session in the afternoon session, where we will build this classifier based on neural network in the TensorFlow library. And then we will apply it to some real news articles. You can feel free to share any news articles on this channel and we'll see how the predictions vary for this particular classifier. And in the later half of the second session, we'll discuss the challenges that we foresee while building such classifier models. So here's the classification intuition. Usually we are given a training data where you have many samples, xi's, and each sample is labeled with a yi. So for an example, in our case, xi's are the news articles, yi's are the labels, that is whether a news article is real or is it fake. On the right-hand side is a simple illustration. So let's consider the green ones are the real articles and the red ones are the fake articles. Here we are showing basically a 2D word vector input. So basically the xi's are two-dimensional here, the inputs that we want to classify. And we can use a softmax or logistic regression to learn this linear decision boundary. So this boundary, which is separating the green class with the red class, is what is of interest to us. We want to find this decision boundary so that then if a new data point comes in, we can classify it in its respective class. And the traditional MLStat approach would approach this particular problem as follows. We would assume that our input data is fixed and we would train a logistic regression model. When I say a softmax or a logistic regression model, it boils down to learning these weight vectors or this particular slope of this line, which will determine the decision boundary in this picture. Once we have learned this decision boundary in the picture, we can then use this model to predict the probability of a new data point. That is P of y given x. Given the new news article, what is its label, whether is it real or fake? This formula looks very daunting, but let's break it down further. This formula exactly captures the essence of a softmax classifier. What we are trying to do here is, first we are making a prediction for class y. That is, we use the decision boundary that we have learned, we multiply it, or we take a dot product with our input data xi, and we make a prediction fy. Now this prediction needs to be normalized to be treated as a probability. That is, each value should be positive and it should sum to 1. So therefore, we apply a softmax function, which is nothing but rescaling of these predictions across all the classes. Once we get these probabilities of y given x, then we can choose the y with the maximum probability. So imagine if the probability of the real label given the news article is 0.7, however, the probability of article being fake is 0.3, then we decide that the article is basically real. For each training example, our objective is to maximize the probability of the correct class. That is, we want to maximize this probability of y given x. If this probability of y given x is higher, then there's a higher chance that we are making the right prediction. Another way to look at this particular formulation is we are minimizing the negative log probability for that particular class. Usually taking logs help in order to stabilize the numerical computations and also helps us in easing this mathematical computation here. Once we have devised this particular loss function, this is also termed as cross-entropy loss in many of the literatures around machine learning. The concept of cross-entropy loss is derived from the information theory literature. Let's assume there's a true probability distribution P, and our model is providing a computed probability of Q. Then the cross entropy that we derive from the distributions P and Q is given by PC log QC summed over all classes. So now imagine here, QC is the model computed probability, but PC is the ground truth probability. And given if we all know for a particular article, whether it's real or it's fake, we know that all the probability mass should be on its right class. So in that case, this probability vector would be just a two-dimensional vector where if the article is real, we'll have 1, 0 as the probability vector. But if the article is fake, we would have a 0, 1 vector describing where the probability mass should appear. If we do the calculation, we substitute the value of this ground truth probability along with the model predicted probability. What we realize is that the only term that is left is the negative log probability of the true class, which is minus log probability of yi given xi. And note that this is essentially what we wanted to minimize, or we wanted to maximize the probability of the correct class. So we want to minimize minus of log probability of y given x, where we try to maximize the probability of y given x. So after we have devised this cross entropy loss function, this particular cross entropy is only for one particular sample. So if you notice here, it is minus of log p of yi given xi. So given a data point, what is the probability of each label for that particular data point? We need, in order to calculate the loss function for entire data set, we sum these probabilities over all the data points. So our formulation had xi comma yi, where we had n data samples. We would sum these over all those n data points to get our loss function. Usually, in order to simplify the notation, people also use matrix notations. So instead of writing a sum of w, wij, xj, that can also be written as f is equals to wi. Okay, so we have our data, we have our loss function, and we have calculated the loss function over an entire data set. But these weight vectors that we initially wanted to learn are still not there. We have used this model predicted probability by randomly initializing some weight vector. So if you look carefully here, the probability of y given x is dependent on this wy and wc. However, we don't yet know what these w's are. And the whole objective of training a machine learning algorithm or a machine learning model is to learn these weight vectors. So how do we learn these weight vectors? In statistical machine learning, usually we consider this weight vector as, and they are denoted by theta parameter. And we calculate the gradient of the loss function with respect to all these theta parameters. That is all the weight vectors that are there in your model. Once we know these gradients for the loss function, you can use your update equation to update your theta parameters. So essentially, you use gradient descent algorithm to calculate your theta nu, that is theta old minus alpha times your gradient. For each parameter, that is the theta vector is a big vector of all the weights in your network, and you compute the gradients for the loss function with respect to each individual parameter, followed by updating each individual parameter using this gradient descent equation. And the question arises, how can we calculate this gradients here? There are usually two methods used. A decade earlier, it was used to be calculated by hand. However, more recently, there are algorithmic methods. There are libraries such as TensorFlow, PyTorch, and Keras, which can be used to calculate these gradients automatically. And we will use today one of such libraries in order to do this gradient calculations. Okay, so cool. We have learned a logistic regression model, and we know how to train it. We know how to compute its loss. We know how to compute its gradients. We know how to calculate its parameters. And after several iterations, we will converge to the right parameters. But the problem is that these softmax or logistic regression models are alone not very powerful. They can give you wonderful linear decision boundaries, but they can be quite limiting sometimes. For instance, consider this data distribution where some of the green data points are spread or distributed in the red classed area. it is very hard to learn a decision boundary just using a linear classification model for such a data distribution. However, in real world, such problems are pretty prevalent, and we want to learn a model which can get these decision boundaries right. And one way to do it is using neural networks. Neural networks can learn much more complex functions using nonlinear decision boundaries. We'll soon go into the details of how neural networks are able to learn these nonlinear decision boundaries. But to just give an intuition, by nonlinear decision boundaries, I mean any random decision boundary between these classes can be learned by these neural networks. And as you can see, this is not just a straight line function. It's very hard to represent this particular decision boundary as a well-known function class. And that's where these neural networks are particularly useful to kind of learn these complex decision boundaries without the engineers to have specify what should be the functional form of the decision boundary, how many constants and how many variables should be there in such a decision boundary function. As engineers, we do not need to know that, but we can train these neural networks to learn these inherent representations and give us these decision boundaries. Cool. So let's get into the details of neural networks, how these neural networks are able to learn such complex nonlinear decision boundaries. And an interesting observation here is that this neuron can be modeled as a binary logistic regression. A neural network derives its motivations from biology, from the concept of neurons in biology. And a neuron, the simplest unit of a neural network, and even in our brain, can be modeled as a binary logistic regression unit that we just learned. So let F be a nonlinear activation function, sigmoid, for instance. A sigmoid function is nothing but a two-dimensional version of a softmax function. So let's say for softmax, we can run that softmax, that is the normalization of probabilities over any number of classes. But if the number of classes reduces to just two, then we can simply use a sigmoid function. W be the weights, B being the biases, and H being the hidden layers, and X are the inputs. Essentially, we can always have a bias feature here. W and B are nothing but the theta vectors that we were talking about a while ago. So W and B are both the trainable parameters that you want to know in order to learn your decision boundaries. So a neuron is basically given this input, it would calculate this output. This H output is nothing but a sigmoid version of W transpose X plus B. The sigmoid function looks similar to what is shown on this particular slide. W and B being the parameters. And another important point here is that this B parameter can also be considered as a class prior. So often sometimes the engineers may know some important aspects or some biases about the problem statement, which they would want to incorporate in their particular model. For such cases where the ML engineer knows something about the data set and wants to incorporate his or her own bias priors into the problem, these biases are essentially very useful in capturing those priors. If the engineer does not have any such priors, this can be also set to 0 or can be considered as a trainable parameter. Okay, so now we have learned about this logistic regression unit, and so simply put, a neural network is nothing but running this several logistic regressions at the same time. So if we feed a vector of inputs through a bunch of logistic regression functions, we get a vectors of output. So for instance, consider here, these are the inputs, x1, x2, x3, and +1 for the bias term. followed, and let's feed these inputs into a layer L1, which maps these 4 inputs to 3 outputs. And this is nothing but passing these 4 inputs to 3 logistic regression neurons, basically. Each of them is computing essentially the same function that we had here. Each neuron there is equivalent to computing this particular function, which is calculating the sigmoid of the linear transformation of the input. That is W transpose X plus B, also referred to as linear transformation of the input. And then we pass it through a sigmoid function to scale down the inputs. But the beauty about this solution is that we don't need to decide ahead of time what variables these logistic regressions are and what are they trying to predict. So if you remember in our previous logistic regression classification problem, I was always using this example of fake news being real or fake, a particular vehicle being fake or real. So that was the variable that I was trying to predict. And I knew it ahead of time that these are my inputs, that is the news article is my input and the labels are real and fake. But what if I don't know ahead of time what my variables needs to be? That's where these neural networks can help us. We don't have to decide ahead of time these variables that the model is trying to predict. Another thing that we can now enhance the complexities of these neural network model is that the output of these neurons can be then treated as input to further another logistic regression layer. So consider here these 3 units that we considered from the previous slide. We add another +1 for a bias layer, particular set of neurons. And then output for these neurons can then be treated as input to the final L3 layer neuron. That will basically again compute the same exact function, but the inputs have changed. The output of the first layer becomes the input for the second layer. Now it is the loss. Sorry. So it is the loss function that will direct what these intermediate hidden variables should be. And in order to do a good job at predicting the target for the next layer, do a training based on these loss functions. Now, if you keep on stacking these logistic regression units one by one for several layers, before you know it, you have a multi-layer neural network. And these multi-layer neural network, popularly known as deep learning neural networks, are currently considered one of the state-of-the-art models for many problems in image processing, language processing, and others. Okay, before I go into more details, I would like to introduce some matrix notations for each layer. So here you have an input layer x1, x2, x3. You have these weights. So this weight W12 is actually giving the output 1 for layer 2 based on the input 2. So basically A1 is affected by x2 due to the weight W12. Similarly here, A3 is affected by the bias term by the weight B3. So here, if you look at this equation, A1 is essentially dependent on x1, x2, x3, and the bias term. And we can do a matrix multiplication or individual multiplication here in this case to compute the value for A1. These equations can also be denoted in the matrix notation as Z equals to Wx plus B, where A is then obtained by passing it through this F function. And you might be wondering why we need this activation function. Why do we need a softmax? Why do we need a sigmoid? But believe me right now, for this particular slide, I'll explain why we need it later. But assume for now that we do compute these linear transformations of the input, that is W11x1, 12x2, 13x3 plus B1. After computing this linear transformation of the input, we pass it through a nonlinear activation function, which will then give you an output for a particular neuron. Okay, so why do we need these nonlinearities, or why do we need to care about softmax or maybe sigmoid or other nonlinearities such as or tanh, etc. Without nonlinearities, these neural networks are nothing more than a logistic regression or a linear classifier problem. Because if you look at it, these are essentially matrix multiplications one after the other. So if I multiply this neuron with a weight vector here, it will help me get the value of A1. If I multiply this value of A1 with another weight vector, I'll get the value at A2. And so on. And essentially, this can be treated as a sequence of weight multiplications. So if we do not apply any nonlinearity or any F function, what we're essentially doing is we are multiplying a bunch of weight vectors to the single input. So we are doing W1, W2, W3, and so on multiplied by X. And this weight vector can be essentially treated as a single linear form. These all weight matrix multiplications can then be treated as a single weight matrix. And if you do not use these nonlinearities, you are essentially left with a giant version of a linear classifier or a logistic regression model. With more layers, they can approximate more complex functions only when you have these nonlinearities incorporated in each of your layers. Okay. So let's go here. There's this neural network with a single hidden layer that I have demonstrated. So here, for example, consider this X input. Museums in Paris are amazing, for example. This is our input. We can again do a linear transformation, Wx plus B, to get and pass it through an activation function F to get the value at this layer H. So H is the output at the hidden layer. Finally, we do again a linear transformation U transpose H to get a final score value. Feel free to ask any questions or interrupt me if you're not following any of these slides. Okay, so
may I ask a question?
yeah, sure.
Yeah. What's the main difference between neural networks and deep learning?
So if you stack a lot of layers, that's when you transition into deep learning framework. I'll cover the backpropagation algorithm or a brief over it in the next couple of slides. And essentially, deep learning frameworks, they suffer from the issues of backpropagation because you have so many layers and so many neurons. That's where the distinction between neural networks and deep learning comes into the play. So structurally speaking, deep networks can be constructed by using a lot of neurons and a lot of layers, stacking them one after the another. To construct a large network known as deep. It is deep in the sense you have a lot of layers stacked one after the another. But algorithmically, they differ in the sense that you have to take care of the backpropagation algorithm much more carefully in deep networks as compared to normal neural networks because of the vanishing gradient problems that we'll cover in a minute. Does that help?
What I got from this is that these neural networks stacked over each other, they give rise to some kind of deep learning, right? This is what I came to understand.
So for instance, here, if you're seeing this neural network, imagine, so let's consider this as a normal neural network. What I'm saying is that structurally, if you stack a lot of layers, so here, this particular neural network has 4 layers. If you stack a lot many layers, tens and 20s of layers, and you also increase the number of neurons in these particular networks, such as, so here the layer 1 has only 4 inputs, layer 2 has 4 neurons, 3 has 3 neurons, and so on. But if you make it much more complex, for example, AlexNet and LeNet, they have many more layers as compared to what is shown here, and many more neurons per layer. Those networks are typically called deep networks in the sense that the number of layers are a lot more, and you have a very deep network to train forward. But we learn about a backpropagation algorithm where the distinctions between neural networks and deep networks is more pronounced.
Yeah, thank you, ma'am. Thank you very much.
So if you remember, I mentioned a couple of slides ago that nowadays there are libraries available which can be used to compute the gradients automatically. So when I was learning the neural networks for the first time, we learned a method to calculate the gradients using the backprop and update those weight parameters by calculating those gradients by hand. But when we went on to implement those models, there are very convenient libraries that are available to help you compute these gradients automatically. And while it is a very good exercise to learn these gradients by hand for smaller problems, it often becomes very hard to compute these gradients for more complex problems in general. And libraries such as TensorFlow, Keras, and PyTorch are readily available these days to compute these gradients for you automatically. So essentially what these softwares are doing is they're representing our neural network equations in the form of a graph. And what does that mean is that you would have source nodes as inputs, and then you would have interior nodes as operations. So here, for example, we had a linear transformation of Wx plus b. So here x is my input, followed by Wx plus b. Here W and X have a dot product operation, which is represented as a node, followed by an addition of a bias term, represented again as an operation node. Now this linear transformation output Z is passed through this activation function f of Z, which is again represented as an interior node here as an operation node for f. The output of this function is then fed into again another operation node, which computes the dot product between the u and the h. So u is another input here, and you take a dot product with f. So u is essentially a weight parameter again here. So if you look, x is our input, s is our output, and w, b, and u are all weight parameters that we are trying to train. And usually how we do the training is we would randomly initialize these weight parameters, that is W, B, and U. So you would choose any random value for these. You will calculate the gradients. You will update these weight parameters based on those gradients using the gradient descent algorithm. And this you do for several iterations until and unless your weight parameters converge. And there are several ways for convergence. For instance, if there is the difference between your weight parameter does not change by more than theta for two iterations, or for n number of iterations, you would stop. Or if your loss function is not reducing more than some delta, then you would stop. So there are several criteria for stopping these iterations once the model parameters have been converged. Okay, so coming to the forward propagation. So I've always been saying we compute these gradients and then we calculate these gradient descent algorithm. We use the gradient descent algorithm to update the weight parameters. So we'll very briefly go over what is the forward pass and the backward pass algorithm and how essentially those are being computed. So by forward propagation, it means is that whatever your weight parameters are currently, let's say W, B, U, whatever those values are, you do a forward pass through your graph. So essentially, you take your inputs, take whatever the values of W are currently, and you compute WX. You add the B to it, whatever the current value of B is, and you get Z. Now with this Z value, it passes it to the activation function, you get H, and with the current value of U, you compute your score function. So edges pass along the results of these operations. Essentially, all of these results of the operations are present on the edges. Now in the back propagation, we would go backwards along these edges and we will now pass the gradients. So if you see the difference in the first forward pass, we are only transmitting the result of the operation. That is, the output of the operation is being passed through these edges. But in the back propagation, the gradients are being passed along these edges. So essentially here, you would pass, you have S, which is U transpose H, and you take its gradient with respect to U, and you would pass that backwards. Then you will have to take its gradient with respect to F, followed by this addition function, essentially giving you gradient of S with respect to B. You will again further pass on the gradients with respect to W to this W load. In order to calculate these gradients, I'm using essentially the chain rule of derivatives. We are interested in calculating the gradients of the loss function with respect to every parameter. So in order to calculate the gradient of S with respect to W, you would first have to calculate the gradient of S with respect to U, because S is a function of U, and H. So you'll have to calculate the gradient of S with respect to U and with respect to H. Now this H is again a function of Z. So you'll have to calculate the derivative of H with respect to Z. And now the Z is a function of W. So you'll calculate the derivative with respect to W. And this chain rule will help you essentially track down the gradient of S given the gradient of W. And the good thing about this is, again, as I said earlier, that these gradient computations are done for you with the help of these deep learning frameworks. And we essentially can use those to our problems. Okay. Next, I would like to go on to the hands-on session. Radha ma'am, how much time is left for this session?
See, I think we still have 1 more hour.
Okay. So let me start the demo session in this particular lecture only.
Okay.
So for the demo, I would request you all to kind of do follow this demo with me. This is a hands-on demo. So you would learn best if you also try along with me the particular model. So in order to share this easily with you, I'll be sharing a link to a folder. This folder will consist of mainly 3 files. Fake news classification Python notebook, and data, that is the fake.csv and true.csv. You can download these on your desktop, followed by uploading it to your Google Drive. I'm assuming everybody here is comfortable using their any Gmail account. If you have, that would be helpful. You can just if you have to log in into your Google account, you have to type Google Drive. You can go here and you can just make a new folder, and whatever name you would want to give. and then you open it, and then you can upload your files, whatever you have downloaded. So for instance, let's say I want to upload this PPT that I have here, and I can just simply upload it. So I'll give you a minute to get set up with this thing. So please feel free to ask any questions if you're having any troubles downloading the data, accessing the data, uploading it to your own Google Drive. But I would humbly request all of you to do this setup, because that would be really helpful for you to kind of follow along all these instructions for the hands-on tutorial.
So Ankita, I see the chat box here, and one person has put that, ma'am, this looks quite advanced. Could you also please discuss on the basic fundamentals of AI? He's from electrical background. Is it possible? I leave it to you. I don't know whether it's really possible.
I can talk a little bit about maybe the classification problem, if that would help. But maybe helping me understand which sections are like more advanced, or which sections you were comfortable with, would help me to kind of go into more details at the right time.
I think right now we can continue with your talk. Let's not disturb the flow. And the person, his name is Avinash, I guess. Again, we can maybe get back to him later on. Is that
Sure.
fine? Huh? Yeah.
Yeah, if it helps, I can also share during the break some of these other resources from which I have personally found useful to understand the concepts of machine learning. So yeah, I'll share those resources as well. So may I know if people have uploaded or have done the setup? Okay. So I'm assuming every one of you could upload, could download basically these file too large. These files are pretty small. These are in MBs. Are you trying over the phone? I would recommend you to kind of use a laptop to do this setup, or a desktop computer, because it would be easier for you to follow as well the tutorial, the rest of the tutorial.
Ma'am, you can go ahead with the session. Probably, I guess few of them have downloaded it because it's, kind of time that you gave. Probably they should have been downloaded. You can go on with the hands-over session, ma'am.
Sure. Cool. Okay. So now once you have downloaded and uploaded it to your own Google Drives, if you click on this IPython notebook, so the file ending with IPynB, you right click over it and you can do an open with Google Colab. So Google Colaboratory is a platform where you can run your machine learning or deep learning or neural network models because Google Colab provides you free access to GPUs. It is particularly encouraged for academic use. So you can basically open a Google Colab notebook. Even if you don't have the existing Colab notebook, you can simply type Google Colab and you will be directed to open a new notebook, and you can click on that to open a notebook, and then you can import all the libraries you want, or you can run your commands that you would like. So for instance, in order to run a particular cell here, you have to do a shift enter, or you can also click on this play button that is visible here. So you can just click on here. Your output of this particular cell will appear here. The good thing about these Jupyter notebooks are nothing but essentially are running your code only, just like your your any other editor like a Visual Studio or other softwares. But the only thing is that this can compile your code cell by cell. So you can execute some small section of your code in a cell at a time. So if I have this whole big notebook where I have lots of code written, I do not need to compile everything in order to get a single output. I can also run portions of my code to get intermediate outputs. So let's say now you have opened this Colab notebook, which I have shared with you. You need to connect it with your Google Drive. So the first two commands here really are connecting, asking permission to mount your Google Drive, to connect your Google Drive with your Google Colab account. So essentially, I'll play this button and it will ask me, I'll give it permission. I'll say connect to Google Drive. It will ask me my Gmail account. I'm using the one I'm signed in with. I'll allow. It may ask you your password if you're already not logged into your Gmail account in that web browser. But if you are, then it will not probably ask you for the password. So this step is essentially doing nothing but allowing this notebook to communicate with this folder where you have your data fake and true.csv. Okay, next with this command, we will just navigate to the tree where I have kept my data. So for exactly follow this command up till here. So I have created a, if you open your Google Drive, I have created a folder called work here, followed by talks, and that's where my data exists. So you can change only this portion of your address to refer to the address that you have, whatever folder name you have created, and wherever exact path of your data you can specify here, and then you can just run this command. Feel free to stop me if you are facing any difficulties with the setup. This is a hands-on tutorial, so I'm willing to go as slow as possible here. Okay, now this is the task one here. We'll understand the problem statement. We have already actually talked about the problem statement. We are trying to build a fake news classifier here. We'll be given news articles. We'll develop a classifier model, and that will help us predict whether it is the news article, is it fake or is it real? Now, before we move on, let's actually look at this data. So you can open it with Google Sheets. This is nothing but an Excel version of Google. So let the data open. Meanwhile, we'll install a bunch of libraries here, which will be useful for us to kind of help navigate through the code. Like I said, TensorFlow is a framework that helps you train the deep learning and other neural network models. And GPU is a graphical processing unit, which helps you do the computations much more faster as compared to a CPU. So the benefit of using a Colab, Google Colab, is that the GPU access is free here. So you don't have to pay anything and you can use it for academic purposes. It gives you some limited time slot when you can, for how long you can access at one go. So maybe you can access it for an hour at one particular timestamp, but you can reconnect it and use it multiple times as well. So here I'm just upgrading to TensorFlow 2.0, which is the latest version. This will take a while, so let it run. Meanwhile, I'll quickly describe some of the libraries that we have here. So plot function, Plotly is basically a graphical library, which will help us do the plotting for different things. These libraries, NLTK, Spacy, WordCloud, GenSim, are libraries for specific to NLP. NLP as in the natural language processing. Why we need natural language processing? Because if you recollect, we are talking about news articles here. And we need a way to convert those news articles into a format that a neural network can accept. So if you see here, neural networks can basically work with numerical data, but a news article would have a text data which needs to be converted back into the numerical version. So we'll need these libraries there to convert the data to numerical version. And the other libraries, for instance, TensorFlow Keras, will provide us some basic units to build a neural network. So this will again take some time. Let me run it, and we have a comment. Kavita, you're asking about a tool. Which tool are you asking about? Are you asking how to run these cells? Because if you can run these cell by just clicking on this play button on the side. So if you see here, if you click inside the cell, you'll see this play button. And if you click on this play button, the cell will execute. Okay, now I've installed all my I think there's some network issue. I'll just quickly do it over again so that it gets correctly installed. So these two cells where you're doing imports and installations, it might take a few minutes, so don't worry, it will run. Okay, so now we've installed all the libraries that we need for today. Next, let's see visualize the data. So here I'm using this pandas library. I've abbreviated it as PD. And then I'm using this function read CSV, which is nothing but an Excel file to read the true data and the fake data. So let's see. Okay. Now you can use the command head to see the top 5 rows for this particular Excel sheet. So if you see here, there are 4 columns in this Excel. There is a title, which is the title of the news article. So a US budget fight looms, Republicans flip, etc. Then the actual text within that particular news article. So whatever the text that is describing what the event happened, the subject of the news, so it is regarding some political news, and the date of its publication, when was this news particularly published. You can also see, let's say, the last 5 entries. So again, there is a title, text, subject, and you see here, there are articles published in 2017. So I have a mini challenge for this particular hands-on session. Let's try out these challenges as well. Can you see how many data samples do we have for each class, that is fake and true? Using these data frames or the Excel sheets, can you identify how many data samples to have per class? Before we go into it, may I know how many of us are comfortable with using Python on a regular basis? Okay, so very few people are, I guess, comfortable with Python. Okay, cool. Cool. So the task here is to just identify how many rows are there in the data DF true and DF fake. So how many news articles are there in the DF true and the DF fake. Feel free to put your speak out if you have the answers. Mayank, you have a question? So anyone has answers like how many articles are there in the true data set? Okay.
23,
So a quick for Ahmed, please go ahead.
Is it 23,481?
That's for fake or for true, you're saying? I guess you're saying for fake.
Yeah. The two
Yeah,
ones are
that's
417.
yeah, that's right. So here a quick way to check is to just use the shape
What is the
function.
basic logic used for the identification of this fake news classification? How does it work using Python?
What is the basic?
How do you check whether some news is fake or not? The kind of I'm asking about the score that you have written.
Yeah, so we will be walking through this entire code. We will know whether it is fake or not. So if you're asking, how do I know DF fake and DF true? In general, how do I know the ground truth? Yeah. So,
Yes.
yeah. So to get the ground truth, this particular data set was released a while ago with Fake News Challenge. Another way to collect, so this data set has been curated manually. So some of the researchers have curated it. The journalists have went over these articles to see whether the article is true or false. And a general way to collect such data set is, so you, let's say, know some news websites which in general publish fake news articles. You can take some articles from those websites and call them fake. Just do a manual check once again to be sure that those are fake. And those websites where, for example, the Hindu, Times of India, etc., which you regularly read and have a high credibility, you can take those articles and call them true.
All right, man.
So this is, but make sure, note that these are ground truth labels. And what we are trying to do here is we're using a supervised learning framework where we are given the data, we're given the labels, and we're trying to learn a relationship between the data and the labels. So here we are trying to learn what is the relationship between the given text of the news article and how is it related to the label of true and fake. And once we have learned that relationship, we can then use this classifier to predict on new news articles. So let's say now for any of the news article that is published today, can I pick and say whether this particular news article is true or false without having to ask any researchers or any manual annotation efforts to kind of know whether a particular news article is fake or true. So can we automate the process of this prediction itself? Okay. You also quickly check if there are null elements that are present. So sometimes some of the rows or some of the columns may be missing in your data. And in that case, you might have to delete those rows in order to avoid any further errors. So you quickly basically check command to check that is using is null. So you type df2.isNull. This will basically give you true or false for each row. So this means that this is not null. If title is false at row 0, it means that some value exists here. And then if you call a sum on top of this function, this is telling that all the sum of all total rows in the column title is 0, which essentially means that there are no elements which are null or NA in this particular data set. You can similarly check it for okay. Now we'll again go and perform some exploratory data analysis. So let's create this entire data set. Right now we have like a segregated data, right? We know that this is true. All the articles in this particular data frame are true and all the articles here are fake. So let's combine them. What I've done here is I've created another column which is called is fake, which will become our Y label that we discussed. And we keep a 1 if the article is fake or otherwise. So sorry, I think here, if the article is true, the fake is 1. And if the article is fake, then is fake is 0. I guess I switched it, but let's keep it as it is. You can assign any label. You can switch the labels as well. It won't affect. You just have to keep the labels consistent across your notebook. Okay, and now we concatenate this data set. So let's add df2 comma df fake. So you can just concatenate. So it's like stacking. So you have, let's say, 50 rows for fake, 50 rows for true real articles. You're just combining them together to make a 100 row data set. So that's all. So here you have now 4,898 rows with 5 columns. So that many news articles you have. Some of them has label 1, some of them would have label 0. Let's delete the date column. I'm not going to use it, so I'm deleting it. You can simply use df.drop columns equals to date. Place equals to true means you affect the data frame in place. There would be no return object. You are changing the df variable itself. Now let's combine the title and the text together because that's what we're going to use later on for data exploration. So it's just essentially a concatenating title and segregating them by space, and then you add the text. And I've created another new column called original. So if you see here, let's see now what the first article looks like. It is about US budget fight looms. Republican flip their fiscal script, Washington Reuters. And then the actual news content is starting on. So it says about Donald President Trump and his Republicans' actions and stuff. So, okay, we have a question chat. Any questions up till now? Okay. Now remember I mentioned that neural networks use numerical data as input, but our news articles are essentially text data. So these are words. And the question arises, how do you give this as an input to a news article? And this particular setting is quite common. If you have heard of maybe if you have used Google Assistant on your phone, or maybe if you might have seen over your Google Gmail. Sometimes when you're writing an email, Google will auto-complete your sentences or would suggest some sentences to you for your emails. And everywhere for these particular use cases, we're using language processing and language understanding, which is a field which basically tries to analyze this text data. So we want to represent this data in a numerical fashion so that we can then run deep learning models or neural networks on top of it, or we can use this particular representation to understand what is the meaning of the text being conveyed. This understanding is for the machines so that they can perform some task on top of it to give us answers. So if you wonder ever, how does your Google Assistant you by telling you what's the weather like today? If you ask your Google Assistant and it replies you, it's like 17 degrees. That's essentially in the background, the Google Assistant is processing your text. That is what's the weather outside, understanding what you're looking for, and then returning the answer to. And that's the major application right now of language processing in the industry. Okay, so now let's see how we can represent this text data into numerical data. If you look carefully for this text data, not all of these words are useful. So for example, the, as, a, the, these words are helping us. These are essentially there for English language construction, but are often not very useful for text understanding. These words are essentially increasing the size of your vocabulary and are present all across all the documents. So the stop words such as is, in, the, etc. These words are going to be present in news articles. So whether it is real or is it fake, it does not matter. All of these words are going to be present in all of those articles, and therefore we can avoid those kind of words in our processing so that we can reduce our vocabulary. So these words are essentially called stop words in the NLP domain. So NLTK is again a library which can help us download stop words. It's nothing but a list of these words that I just mentioned. So you can run this to download. And then you can list all these stop words .words from English language. So let's say now I can see words like I, me, my, myself, we, our. These are the words which would be common in all the news articles, whether it is fake or it is it's. So these words will be safely removed analysis. So let's do this pre-processing. We will remove these stop words and we will remove words with 2 or less characters. So words with 2 or less characters are often punctuation marks or emojis, smileys, etc., which may not be very useful in analysis of our reaction. So essentially, we remove these. So for each sim library is just doing a tokenization. By tokenization, I mean splitting a sentence into a sequence of words. So it get the tokens from this text. And then for each token, if it is not in the stop words and its length is more than 3, then you would return that token, otherwise you will discard it. Let's just first see how a text looks like. So have the sentence, John went to the store, and this sentence has broken down into tokens, which is words essentially John went store. And now for each of these tokens, what I'm doing is it should not be in the stop words and its length should be more than 3. Then I'm keeping that token, otherwise I'm removing that token. So let's run this function. So if you see, to and the were actually present in our stop words, and their length was also, so to had a length of only 2 characters. So therefore it was discarded. A the was present in the stop words, was again discarded. So this is the output. Now we have tokens which are essentially more than 2 characters long and are also not very common across all of these news articles. Now we will apply this function preprocess to all of the data that we have. So df of original dot apply preprocess. This would basically do sequentially one by one for all rows, apply this function preprocess, and we'll keep it in a column called clean. So this is gonna take a little while because it is doing a sequential update for more than 44,000 rows. So this will take a little bit of time. Now, meanwhile, if you have any questions, please let me know. Okay, so we have this clean data here. Now we'll quickly see how the original looked like. This is how our original data was, which we saw earlier. And let's now see again how the clean looks like. So if you see words like as, US, so budget, this is 2 characters, more than 2 characters long. Budget, fight, looms, etc. These are all kept. Some of these words are removed. Whichever was satisfying this criteria, that it should not be in stop words, and then it should be more than 3 tokens long. Okay, so now we have this data. So now let's look at how our actual data, the entire Excel sheet looks like. So we have title, text, subject, original, and then we have clean column where all of these tokens are present from this particular text. So for example, here if you see 10 US Navy sailors held by Iranian military, if you see the words like Navy, sailors, held, Iranian, etc. are all present. Words like 10 and US have been removed. So essentially I removed US here because this data set is particularly about US news articles, and US is going to be mentioned for most of these articles. So it's not a full indicator of whether a news is fake or not. So if you have any such prior knowledge, you can use it during your data pre-processing step to kind of remove any things that you feel might give useless correlation, such as the words US, or maybe if it's an Indian news, India would be or a particular state news, so you can remove those names of the state, etc. Yeah, Mayanka, I would be happy to talk maybe during the last few minutes of the session. Okay. Okay, now let's see. I would want to know what is the total vocabulary size. So we will find all of these words that we have in our entire data set. So this is the list of entire words. And if we see how many words we have is, we have 92,000. Okay, we have a lot of words in our entire data set, but essentially these many words are not needed, or many of those words are repeated across the data sets. So we are usually interested in finding a vocabulary of all these words, that is the unique words that appear in this data sets. So let's find all of these unique words. So the set operator will tell you unique words in the list of words. And this list would just convert a set data structure back to list data structure. And this tells us that it has approximately 1,08,705 total words. Okay, so now we have that. Keeping this in mind, let's now combine all of our data set. So right now we have these tokens here. The reason why I'm interested in finding a vocabulary is because later on I will assign each of these tokens an index based on the vocabulary. So let's say for each word in your vocabulary, you assign it an index, like word A is index 1, B is index 2, C is index 3, and so on. And then if a particular news article has a particular word appearing, you can replace this word by that particular index. And that's how essentially you convert a text data into its numerical version. We will first now convert back this splitted clean data into its string version. So essentially, let's say I had this John store. These are the tokens that we have. And what essentially I'm trying to do is convert back this to string. So John to the store. So this is like again coming back to its string. It will become clear why we want that. Let's run this line, which will take some time. Okay, done. So each coming up here, it's asking us to visualize at least 3 sample news articles. So pick up any news article from your DF data. You can look for this particular column, clean joined. And in order to check a particular news article, you can use any index here to just read it. So feel free to kind of check any 3 sample news articles. Okay, so Radha ma'am, I would like to actually take the break now to kind of keep the flow for the next session.
Ms. Sankita,
Yeah.
we can take a break and probably we can meet by 11:30.
Yeah, sure.
Now it's 11:20, so probably we can meet by 11:30. I request all the participants to just have a break for about 10 minutes and we shall be meeting back in another 10 minutes from now on. So kindly do not log out. So please be online with your logins and we shall meet in another 10 minutes.